And welcome back. As we go ahead and look at our next review lesson, let's go ahead and talk about functions and graphs. Now, previously we had assumed some familiarity with the language of functions and graphs, and we use that to kind of connect in with lines in the coordinate plane with their algebraic representations so we could create linear functions. Let's go ahead and expand on those terminologies, though, with some of the language that we're going to need to know. The first thing, of course, is when we start talking about a function, it is a set from set D to set R, and is a rule that's going to assign every element in D to a unique element in R. All right, and you probably already know that D, of course, is referring to the domain of a function, and R is referring to the range of a function. Now, in function notation, we are going to use not y equals, but we're going to use f of x. And that's going to denote the range of a function that is assigned to that domain x. And when we look at the set of all points, x and y, that are in the coordinate plane determined by that function rule y equals f of x, we are going to simply refer this to the graph of the function f. The variable x, of course, when we talk about functions, is the independent variable, and y is the dependent variable. Now, most of the functions that we look at in this course are going to be mapped from the real number set to the real number set. We're not going to have to worry about complex numbers. So in this context, the domain is a subset, not always the entire set, of the real number set, as is the range. And again, the denotation y equals f of x is a way for us to note specific values of a function. So let's go ahead and look at this with an example. So we're going to, of course, write a function that expresses the area of a circle as a function of its radius. And then we can use that formula to find the area of a circle with a radius of 2 inches. Well, if we recall, the area of a circle is a pretty common function. We know that the area, and because we're using this as a function of its radius, that means we need to say area of r, we'll use r for radius, is equal to pi times r squared. Now that we have that function written, of course, we can use that to find a circle with a radius of 2 inches. So if we go ahead and just plug that in, we can say the area for a value of 2 is going to be equal to pi times 2 squared, which means that the value should be 4 pi. All right, and of course we wanted to express this in units. We could say that our answer is 4 pi inches squared. When we define a function with a formula and the domain is either not stated or restricted, it's assumed to be the large set of x values for which the formula can give us real y values. This is known as an implied domain. Now, if the domain is restricted by context, such as previous example, all right, where we can say, hey, you know what, we have to have a radius, and the radius, as we know, are going to be non-negative, then we can say that we have what's known as a relevant domain. Now, note that domains can be restricted as part of their definition. We can, for example, say it's only going to be positive integers. Now, the domain and ranges of many real valued functions of a real variable are intervals or some combination of intervals. Now, these intervals might be open, closed, half open, and they're either finite or infinite. So, for example, you start looking at these here, you can see we have a couple different representations of these different intervals. And you'll notice we have in here endpoints. Endpoints of an interval make up the interval's boundary and are also referred to as boundary points. Then all the remaining points are making up the interval's interior, so the area in between point A and point B. And these are referred to as interior points. So if I had another point here, let's just say, and we had the C, C would be an interior point. Now, closed intervals contain their boundary points. Closed intervals, for example, would be like this A here, or this B here. Or I can look at this A here, this B here. They're all closed because you can see the circles filled in. Now, open intervals contain no boundary points. And every point of open interval is an interior point of the interval. So again, looking at these right here, so this A and B, for example, would be an open interval. As with this B, would be an open interval. Now, when we start viewing and interpreting graphs, the points x, y in a plane whose coordinates are the input-output pairs of a function, y equals f of x, make up the function's graph. For example, if we look at the graph of the function y equals x plus 2, it is the set of points with the coordinates x, y, for which every y is equal to x plus 2. So let's do a little practice with this for our next example. So let's identify the domain and range of function. We want to identify the domain and range of these two functions, and then we're going to sketch a graph of them. So if we start first with y equals 1 over x. So this means that we are, of course, going to have a look at this and start thinking, all right, what are the domain values that we can put in here? And then the same thing here. So let's start first. I'm going to start first with the domain, and then let's map the range. And so I'm actually just going to do this so we can do both questions here. And I'll just make a nice little line. So the domain of this function, if you think about it, our domain is going to be, for our first function, going to happen all the way to, theoretically, any value except for what? Well, we cannot have 0 in here, because if I put 0 in here, we're going to get a problem. So I can't plug in 0, which means I have a spot there where I need to exclude from my values. So this means I can have a value that goes from negative infinity all the way up to 0. And I can also say that is going to then restart at 0 and go to positive infinity. And again, remember, we are not including 0, so that's why we don't have a square bracket here. This is a type of notation you might want to get familiar with. And when we start talking about range, we start thinking, okay, well, what range can we have here? All right. Well, again, if we start thinking about our range, it's also going to be very similar because, again, if we try plugging in that 0 values, we have problems. You can't get this graph to end up at 0. So our range is, again, going to be very similar. We're going to go from negative infinity to 0. And we're going to go from 0 to positive infinity. If we look at the square root function, we're going to have something slightly different here, because when we start looking at this one, we're going to give a real number, because again, we're restricted to the real number set, only when x is either positive or it's 0. And because of that, it means any negatives will not be included in this. So our domain needs to be, and I'm going to use a square bracket this time to denote a closed interval here. So this is going to be from 0 all the way to infinity. And again, I can use a regular parenthesis here. And what about our range? Well, our range, if you think about it, is going to be the same set of values. We're going to have a value that's going to start at 0 and is going to go to infinity. And so if we graph these, all right, if I make a kind of a crude sketch here of this graph here, I'm just going to do a crude one real quick. 1 over x, of course, is going to look something like this. Again, this is not an exact graph of it. I'm just doing a quick sketch one here. And the square root of x is going to look something more like this. And again, you can make these more accurate by plugging in your calculator, but for our demonstration purposes here, we can do that. Again, I could easily grab my calculator to get more accurate representation of what these functions look like. So let me just head on over to my two functions here, just so you can see those for reference. So I'm just going to do 1 over x. And then let's go ahead and make this one the square root of x. And let's make sure this is set to the standard. And you can see here is our 1 over x function, and here's our square root of x function. All right, so let's do define the domain range now, but using a graphing calculator. Because the first two functions we looked at were very simple that we could look at and easily pick apart. But what about something that's a little more complex, like x to the 2/3, or the square root of 4 minus x squared? So what we're going to do for these two is we're going to grab that graphing calculator again. I'm going to go ahead and let's clear these two functions out and set it up with those two functions. So I have x to the power of 2 over 3, so I'm going to do x to the power of, I'm going to do parentheses, 2 over 3. And then our second one is the square root of 4 minus x squared. All right, if we go ahead and graph those, make sure that's a square there. we can watch our first function coming in. And you can see we have kind of this bow shape here. And here's our second function, of course, almost like a semicircle appearing right here. Let's just go ahead and zoom this in just a little bit here. So I'm going to go ahead and change my window. Let's just make this a x is negative 5 of 5. And let's do something similar here with our y values so we can, again, get a little bit closer view of that function. So I'm going to go ahead and regraph that. And again, you can see with our first function, y equals x to the power of 2/3. We, of course, have this function here. And also, you can see now, there's also, now that we zoomed in, we can see that this function doesn't quite meet in some of those areas. This is very important because it starts allowing us to look at some of these values here. So let's first look at the very first function. And we can trace this here to kind of try and see where this function is. You can see it is intercepting here at 0, 0. So it hits the origin. And as we trace through this, you can see we have values that are going to be staying for our y values. They're always going to be positive, which kind of makes sense because of this exponent that we have here. If I switch to my other function and I start tracing this, and I watch those y values, notice it is now y is undefined. Once I reach a certain point, come back, y is now defined, which also means that that y function is never going below a certain threshold. So when we start saying, okay, well, what actually is the domain and range here? Going to this first function here, if we wanted to figure out what is the domain of this function here, it's pretty easy to look at because we can, again, look at this. We saw how the graph looks like it's traversing every value, but where it changes is in a range. So our domain is pretty simple. We can simply just say that it's going from negative infinity to infinity. And our range is kind of following something similar, except it never crosses below 0. And because it doesn't cross below 0, that means we have a closed interval here. So I'm going to use 0 here. And it's going to go, technically, to infinity. Now, what about this other function that we have here? Well, our other function, remember, was kind of a semicircle sort of shape. And when we look at this, we have to look, okay, what is our domain that we can actually plug in here? Well, for us to actually think about this, we have to think about this square root. And if we start thinking about this algebraically, if we want to have a value in here that's not going to make a negative square root, what is the maximum value that we can plug in for x? Well, we have 4 minus something. What is 4 minus something squared? That would be 0. That would be 2. Which means that the values that I could plug in here would have to be from a value of negative 2, because remember, negative 2 squared is positive 4, all the way to positive 2. And therefore, when we start asking about the range of that equivalent function, we go back and look at that graph. All right, we can see that we are effectively, even though we have some decimals and stuff in here, we could, of course, zoom this in and try and find it even closer. But we do seem to have kind of a hard cap here on our trace as we move through this, because even though this function is going up, 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 it never quite crosses this y equals 2, because this is the intercept right here. So we're going to go ahead and say that the range of this function is going to go from 0 to 2. Because again, remember, if we plug in a negative 2 here, what do we get? We have negative 2 squared is 4. 4 minus 4 is 0. And we plug in 2. 2 squared is 4. 4 minus 4 is 0. So that would have to be the smallest value for our range. Now, these, of course, are nice things to kind of keep in mind. But one of the things that's going to really help us out is when we start looking at the difference between even and odd functions. And the graphs of even and odd functions have important symmetry properties. So, for example, if we look at an even function, that means when we say y equals f of x, we're going to say, hey, it's an even function when f of negative x is the same as x, and it's an odd function when f of negative x is equal to a negative x for every x in that domain. Now, the terms even and odd typically come from the powers that are associated with x. So, for example, if y is an even power of x, such as y equals x squared, and you can see right here is our squared part, then it is an even function. If y is an odd power, such as y equals x cubed, again, we're looking right here at that odd number that's there, we have an odd function. Now, the thing to keep in mind with these functions is that graphs of an even function, all right, are typically going to be symmetric about the y-axis, whereas graphs of odd functions are symmetric about the origin. Remember, origin means 0, 0. All right, so that's an important thing to keep in mind. So let's look at these functions real quick here and see if we can identify whether these are even or odd functions. Well, the first one is real simple to look at. I can look here. I have a power right here. And actually, I'm going to switch to different colors just so that we can highlight this a little differently. So I have an x squared that is a positive number, which means this has to be an even function. I look here. Okay, f of x equals 2x squared plus 1. Okay, what does that mean I do? Well, again, I'm just simply going to look at what is the biggest power here. Because even though the other powers can affect it, whatever the biggest one is going to be the one that kind of dictates the rules of how this function acts. So with 2x squared plus 4, this should be an even function. And I can easily verify that by coming over to my calculator. And I can plug that in. And so let's just go ahead and plug in. I have 2x to the power of 4. And I'm going to add 1. And we should see a function that is parabolic in shape. All that plus 1 did is simply shift that up 1 the axis. The function itself, you notice, is still symmetric about the y-axis, which means it's still an even function. All right, what about 5x cubed plus x? Now, again, this is technically x to the power of 1, but we are simply going to look at the largest power here, 5x cubed. This means this should be an odd function. And again, we can verify that very easily by coming on over here, and I could plug this in. Now, the one thing I want to point out is this last one, 3x minus 5, because even though x is to the first power, does that mean that it is an odd function? And this is a thing of caution I want to give you, because when I plug this function in, notice it is a line, but remember, for it to be an odd function, it needs to operate around the origin. This function does not operate around the origin, which means this is neither. So this is something to kind of keep in mind here if you're working with linear functions. If you had something like, let's say, y equals x, so let's just do y equals x, let's say, and I'm just going to delete the rest of this out. This one would be an odd function because it does pass through the origin, and you could rotate it around the origin. So little things to keep in mind there if you're looking at the difference between even and odd functions. Now, the other type of functions we got to keep track of are things such as piecewise functions. And these are important because while some functions we can define with a single formula, so like y equals x squared, other formulas are going to be applied across different parts of the domains. So, for example, in example 5 here, we're using y equals, and you can see we have negative x for x is less than 0, x squared for when it's between 0 and 1, and we have the value 1 when it is greater than 1. So let's go ahead and take this function then and plot that in. So I'm just going to go ahead and bring up my canvas here. So let's go ahead and graph this function. So I have y equals, and for x is less than 0, I have negative x, which means this function should be decreasing through here. So this is going to end at 0. Notice it's less than, which means I need a closed interval in here. And this is going to just simply come right on through here. And then we're going to switch from 0 to 1, and I'm going to have closed intervals here. So this part is a closed interval, and it's going to go to 1. And this is a squared function, so again, we're going to have kind of that curved part here. And then lastly, when x is greater than 1, we're going to, that part will be an open interval, but we're going to go ahead and have that function simply go out at 1. And that's the 3 segments that we have in this piecewise function. What about actually writing our own piecewise function? Well, in here in this next graph, you can see that we have 2 different line segments, and we want to create our piecewise function for this. So let's go ahead and say, well, we have a function. So let's just say f of x, and we have 2 pieces here. So I have 2 pieces of this function. And so looks like these are closed intervals because I don't see any open circles. So let's just go ahead and assume that these are closed intervals here because again, there's no open circle to indicate that these are not included points. So our first function is simply coming straight down. So that part we can say is a negative x, and that is for when x is less than or equal to 0. What about the other half of this function? Well, this part of the function, if we look at our rise over run here, looks like we are moving 2 over and 1 up, which means we have a function that says we are probably going at about 1/2 slope here, because you know it's going up half the speed. So we have a 1/2 x, and notice that we also started up higher, so that is plus 3, and that should be for when x is going to be greater than or equal to 1. Notice there are no values from 0 to 1, and that is an important distinction here of things you can do with a piecewise function, because in these values nothing exists in this range. Alright, so this conversation about piecemeal is very important because one of the things we might talk about is like absolute value functions. And absolute value functions, which are we define as y equals the absolute value of x, means that when we look at the negative values of x, that means x is less than 0, and the positive values of x are for when x is greater than or equal to 0. Now, the thing to keep in mind with an absolute value function is that it is technically an even function because the graph is symmetric about the y-axis. So let's do a little transformation work on that basic function. So we have draw the graph of f of x equals the absolute value of x minus 2 minus 1, and then we want to find the domain and range. So to help us out here, one of the things you can do, if you're like, I'm really stumped on this, you can always grab your graphing calculator real quick here, and let's go ahead and plug that on into this function. So I'm just going to go ahead and clear it out, and let's go ahead and grab the absolute value of, we want x minus 2, and then we're going to do minus 1. We know that minus 1 is going to cause a shift, so we can already anticipate that. But what that is going to do, if we look at that minus 2, what did that do? Well, that caused a shift in the horizontal direction, and the minus 1 caused a shift in the vertical direction. So let's go ahead and transfer that. So we have here a value that says, okay, we went 2. So we're going to move that first point over to 2 and down 1, because that minus 2, remember, means that minus 2 means a plus 2 in the x direction, and that minus 1 means a minus 1 in the y direction. And so then from there we can very easily draw the rest of the function just as we saw here. So I'm going to go ahead, switch this back over to my pen, and then I can have that function come through. I'm again just going to kind of make a rough depiction of this function just so you can kind of get a rough idea. Again, the graphing calculator can give you a much more accurate representation than my freehand here. Now, the last thing we have to do, of course, is find the domain range. Well, if we look at this function, our domain of this function should be pretty much all the real values. So I'm going to say the domain is going to go from negative infinity to positive infinity. And our range, though, is not going to be that, because you look, we have a smallest value here. So our range has to be from negative 1 to infinity. Now, the last thing to touch on is composite functions. So suppose that some of our outputs of a function g can be used as inputs of function f. We can then link g and f to form a new function whose inputs are the inputs of g and whose outputs are the numbers f of g of x. Therefore, we can say the function f of g of x is a composite function of g of f. Think about this as you're taking the results of one function and you're plugging it into a second. We can also notate this as f of g of x. So we want to find a formula for f of g of x if g of x is equal to x squared and f of x is equal to x minus 7. And then lastly, we want to find f of g of 2. So first thing we're going to do is take this x squared and we're going to plug it in for x. And all that means is anywhere we see an x, we're going to plug in x squared. So I'm just doing a little basic substitution here. So we can say that f of x, all right, that's the function that we want to have. Remember, is x minus 7. So when I plug in f of g of x, that means that this is now going to change into a x squared minus 7. And so that should, of course, give you the final version of x squared minus 7 for my f of g of x. And so then if I want to find 2, all I'm going to do is say f of g of 2 is then equal to, and I could use this function that I created here, that's 2 squared minus 7. So we get 4 minus 7, which gives us a final value of negative 3.